Welcome to the world of real-time embedded systems, where microcontrollers must respond to events in predictable, deterministic time. FreeRTOS is a small, portable, open-source, real-time kernel designed precisely for this purpose. It has become one of the most widely deployed kernels in the world, running on more than 40 processor architectures and shipped with over 20 compilers. This section explains why a developer would choose an RTOS at all. The answer is simple. An RTOS lets you structure complex applications as independent tasks, each with its own priority, instead of wrestling with a single tangled superloop. FreeRTOS offers a minimal footprint, a permissive MIT license, and a clear upgrade path to the commercially supported OpenRTOS and the safety-certified SafeRTOS. By the end of this series, you will understand not just the APIs, but the philosophy behind it. Before writing a single line of application code, a developer must understand the FreeRTOS distribution itself. This section is your map. It explains the concept of a port, a specific combination of compiler and processor for which the kernel has been adapted. It walks through the source files common to every port, the files specific to each port, and the all-important configuration header, which tailors the kernel to your application. Demo projects are provided for every supported port, and this section strongly recommends starting with one of those rather than building from scratch. You will also find guidance on data types, naming conventions, and the rationale behind FreeRTOS's distinctive coding style, including its deliberate use of typecasting. Understanding the layout of the distribution is the first practical step towards a working FreeRTOS project. In embedded systems, memory is precious, and how you allocate it can make or break your design. This section introduces FreeRTOS's flexible approach to memory management. Kernel objects such as tasks, queues, and semaphores can be allocated either statically at compile time or dynamically at runtime. Static allocation is deterministic and avoids heap fragmentation. Dynamic allocation simplifies the APIs and minimizes the RAM footprint. FreeRTOS ships with 5 heap management implementations, Heap 1 through Heap 5, each with different trade-offs in speed, fragmentation resistance, and complexity. Heap 1 is the simplest, and it never frees memory. Heap 4 is the most popular general-purpose choice. Heap 5 supports non-contiguous memory regions. This section also covers utility functions for monitoring heap usage and detecting allocation failures. Choosing the right scheme is a fundamental design decision that shapes the reliability of your entire application. A task in FreeRTOS is a small C function that runs forever in its own context, with its own stack and its own assigned priority. The scheduler decides which task runs at any moment based on priority and state. Tasks move between 4 states: running, ready, blocked, and suspended. This section has information about how to create tasks, how to delay them, how to change their priority, and how to delete them safely. It explains the tick interrupt that drives the scheduler, the idle task that runs when nothing else can, and 3 scheduling algorithms: preemptive with time slicing, preemptive without time slicing, and cooperative. Task management is the foundation of any FreeRTOS application. Tasks must communicate, and queues are FreeRTOS's primary mechanism for doing so safely. A queue is a fixed-length, first-in, first-out buffer that holds fixed size data items. Any number of tasks can write to it, and any number of tasks can read from it. When a task tries to read from an empty queue, it can block, sleeping efficiently while data arrives or a timeout expires. When a task writes to a full queue, it can likewise block until space frees up. FreeRTOS deliberately uses queue by copy rather than queue by reference, simplifying ownership, eliminating coupling between sender and receiver, and allowing data to cross memory protection boundaries. This section walks through creating queues, sending and receiving data, blocking semantics, and the powerful technique of blocking on multiple queues at once using queue sets. Queues are the lifeblood of inter-task communication. Many real-time systems need to perform an action at a specified time in future or repeatedly at a fixed frequency. FreeRTOS provides software timers for exactly this purpose. A software timer is a kernel-managed object that, when it expires, calls a user-supplied callback function. There are two kinds: one-shot timers that fire once, and auto-reload timers that fire repeatedly. Crucially, software timers consume no CPU time unless a callback is actually executing. They piggyback on a single daemon task that the kernel creates automatically. Commands to start, stop, reset, or change a timer's period are sent through a command queue, keeping the API safe for use from both tasks and interrupts. This section emphasizes one strict rule: timer callbacks must never block, because blocking the daemon task would freeze every timer in the system. Embedded systems live and die by the handling of interrupts, those asynchronous hardware events that demand immediate attention. This section draws a sharp line between two worlds: tasks, whose priorities the software scheduler controls, and interrupts, whose priorities the hardware controls. Interrupts always preempt tasks. This section explains the interrupt safe API. Every blocking FreeRTOS function has a from ISR variant designed for use inside interrupt service routines. It teaches the powerful pattern of deferred interrupt processing, where the ISR does only the bare minimum and hands the real work off to a task using a binary or a counting semaphore. This section also shows how queues carry data between ISRs and tasks, and how interrupt nesting works on supporting ports. Keep ISR short, defer the heavy lifting, and your system will remain responsive under the load. When multiple tasks share a resource, a peripheral, a memory location, a hardware register, concurrency becomes dangerous. This section talks about how two tasks clobbering each other's read, modify, write updates of a port register can be avoided. The solutions are the classic tools of concurrent programming adapted for FreeRTOS. Critical section: briefly disable interrupts. Suspending the scheduler prevents the task switches without affecting the interrupts. Mutexes provide mutual exclusion with priority inheritance, which protects against priority inversion, the notorious bug that crashed the Mars Pathfinder. Recursive mutexes allow a task to acquire the same lock more than once. This section also explains gatekeeper tasks, where a single dedicated task owns a resource, serializes all access. When these tools are used wisely, shared resources stay consistent. Semaphores and queues unblock one task at a time in response to a single event. But what if you need to wait for several events at once, or broadcast a single event to many tasks? That is what event groups are for. An event group is simply a set of bits packed into one variable, typically 24 bits on a 32-bit machine. Each bit represents an event flag. Tasks can set bits, clear bits, or wait in the block state for any combination of bits to become set, whether through logical AND or logical OR. This section shows how event groups enable powerful patterns, synchronizing multiple tasks at a rendezvous point, broadcasting a shutdown signal, or waiting for several independent subsystems to finish initializing. Event groups can also replace many binary semaphores, saving valuable RAM. Every communication mechanism described so far, queues, semaphores, event groups, requires a separate kernel object sitting between sender and receiver. Task notifications take a different approach. They send the signal directly to the target task itself. Each task has a notification state and a 32-bit notification value built into its task control block. Sending a notification is much faster than any equivalent queue or semaphore operation, often by a factor of 45% or more. And it uses dramatically less RAM. Since no separate object needs to be created, notifications can act as lightweight binary semaphores, counting semaphores, mailboxes carrying a single 32-bit value, or even mini-event groups. The limitation is symmetry. Notifications only work for direct point-to-point communication with a single known receiving task. When that fits your design, nothing is faster or leaner. Battery-powered devices must squeeze every microamp from their microcontrollers, and FreeRTOS makes that possible without sacrificing real-time behavior. The simplest approach is the idle task hook, where you place the processor into a light sleep mode whenever no task is running. But the more powerful technique is tickless idle. Normally, the tick interrupt fires hundreds or thousands of times per second, waking the processor on every tick. In tickless idle mode, the kernel suppresses the tick interrupt entirely during idle periods and lets the processor enter a deep state until either an interrupt arrives or a task is due to be woken. When the processor wakes, the kernel corrects the tick count to account for the time spent asleep. This section shows how to enable, configure, and customize tickless idle for genuinely long battery life. Building a working RTOS application is one thing. Debugging it is another entirely. This section assembles FreeRTOS's toolkit for catching errors and gaining insight. At the top of the list is config-assert, a macro the FreeRTOS source code peppers liberally throughout itself to verify assumptions at runtime. Defining it during development will trap an enormous fraction of bugs the moment they occur. The section also covers Stack Overflow detection, tracehook macros that let external tools like Tracealyzer visualize every context switch and kernel event. This way, you will learn about runtime statistics that show exactly how much CPU each task consumes, and a task list dump that reports the state and stack high watermark of every task in the system. These features turn debugging from guesswork into engineering. This is the last section, which is troubleshooting. This section talks about the mistakes FreeRTOS users make most often. Number one, by a wide margin, is incorrect interrupt priority assignment, particularly on ARM Cortex processors where numerically high values mean logically low priorities, and where priority bits may need shifting before they reach the hardware. Misconfigure this, and the critical sections silently fail. Number 2 is stack overflow. Each task has its own stack, and sizing it requires care. Number 3 is inappropriate use of printf inside tasks or ISRs, where it can consume vast amounts of stack or block unexpectedly. This concludes FreeRTOS series. Thank you.